Public debate often misinterprets rare earth scarcity. The term rare suggests a geological shortage, but these elements are abundant throughout the Earth's crust. This chart compares the crustal abundance of elements in parts per million. Cerium, lanthanum, and neodymium exist in quantities similar to major industrial metals like copper, zinc, and nickel. Their lithophile behavior drives this broad distribution. Rare earth elements bond with silicates, phosphates, and carbonates, dispersing thinly across resistant crystal lattices rather than accumulating in high-grade metallic veins. The true global supply constraint is an industrial bottleneck. Most of the world's production capacity is tied up in complex hydrometallurgical processing and separation, which are required to isolate these elements from one another. Mining raw oxide concentrates is merely the initial phase. Reaching to high-purity elements found in these vials requires a specialized, resource-intensive separation chain. The physics of the 4F electron shell dictates the structure of this entire supply chain and explains why these elements are so difficult to isolate. The perceived scarcity of rare earths is a metallurgical constraint of quantum mechanics, existing within the processing facility rather than the ground. Under natural conditions, these elements favor a trivalent, or 3+ oxidation state. Removing exactly 3 electrons is the most energetically efficient pathway for this group. The 4F shell defines the lanthanide series. In gadolinium, it sits deep within the atomic structure. Filled 5s and 5p orbitals completely shield these 4F electrons, acting as a physical barrier. Because this core is protected, the lanthanides behave as nearly identical chemical entities. As the atomic number rises across the series, the nucleus gained protons, which increases the effective nuclear charge pulling on the electrons. This graph plots atomic number against ionic radius. The rising nuclear charge steadily compresses the 4F orbitals, creating the lanthanide contraction. This produces minute size differences between the elements, often measured in fractions of an angstrom, 1/10 billionth of a meter. Standard chemical reactions cannot distinguish these elements. The microscopic size differences created by the lanthanide contraction provide the only functional lever available to separate them. Nature uses this strict size constraint to sort these elements during the slow, intense crystallization of deep underground magma chambers. Light rare earth elements occupy the beginning of the series and possess larger ionic radii. This results in lower charge density and weaker electrostatic attraction. Their larger size allows light rare earths to partition into early magmatic minerals with spacious 9-fold coordination sites, like bastnaesite. Heavy rare earth elements have smaller ionic radii, resulting in a higher charge density. This high charge density creates stronger electrostatic interactions, forcing heavy rare earths into tighter 8-fold sites, like those found in xenotime. This same radius-controlled behavior governs the formation of ion-adsorption clays on the surface. In subtropical regions, millennia of intense, prolonged weathering dissolve granitic rocks, releasing these trapped elements directly into the rich soil profiles. Heavy rare earths bind to these clay surfaces through outer sphere electrostatic forces, driven by their high charge density. Surface clays allow for simple salt leaching at ambient temperatures. In contrast, light rare earths in hard rock require aggressive, high-temperature digestion to break their crystal lattices. A fraction of an angstrom determines if an element can be washed from surface clay, or if it remains locked in a refractory phosphate lattice deep underground. Carbonatite open-pit mining requires moving massive tonnages of rock to capture trace concentrations of rare earth oxides. A high geological grade does not ensure a high-quality deposit. The specific mineralogy dictates whether the ore can actually be processed. Bastnaesite follows a predictable beneficiation pathway: flotation, calcination to remove carbon dioxide, and direct acid digestion. Beneficiation separates the valuable mineral from the worthless gang rock. Eudialyte processing is much more complex. Chloride leaching on this mineral triggers the formation of a silica gel that clogs recovery equipment and halts the circuit. Hard rock phosphates like monazite possess high lattice binding energies, making them resistant to chemical attack. Monazite also incorporates thorium and uranium for charge balance, which necessitates strict radiological handling and waste management. Mineralogical resistance and impurity load define the viability of a deposit. Even at high concentrations, refractory or highly radioactive ore can be economically worthless. Once dissolved into a liquid solution, the rare earths must still be separated from one another. Engineers use organophosphorus extractants to exploit the tiny differences in ionic radii. Heavy rare earth ions move into the organic phase more readily because their higher charge density creates stronger interactions with the extractant molecules. Because separation factors between adjacent elements are so narrow, a single extraction stage is highly inefficient. The atomic similarity of these elements forces a massive industrial response, requiring hundreds of mixer settlers arranged in a continuous countercurrent series. Maintaining phase stability across these vast circuits requires enormous amounts of capital, chemical reagents, and environmental oversight. High-purity rare earth oxides are the result of intense chemical engineering designed to overcome near-identical atomic behavior. These refined oxides are fabricated into the permanent magnets used in electric motors, wind turbines, and precision-guided munitions. The global scarcity of separated rare earth metals reflects a limitation of processing throughput, rather than a lack of geological resources. The immense capital and chemical intensity of solvent extraction centralize the supply chain within a few jurisdictions. Successful extraction depends on the rare alignment of favorable mineralogy, low radiological impurities, and billions of dollars in hydrometallurgical infrastructure. Modern technological geopolitics follow the stubborn, shielded chemistry of the 4F electron shell.